ch28.4, the relativity of length, or also length contraction. This is another consequence of the speed of light being constant in all reference frames. Time will change, and now also length or distances are going to change. The only thing constant is our speed of light. So the length contraction is this idea of the shortening of distances between 2 points. What does this mean? Well, it in part depends on your perspective. But basically, if you see something moving fast, then the length, because as it moves faster and faster, the length of it in the direction that it's moving appears to be shorter. So from Earth, when it's looking at a spaceship, Earth sees a spaceship get much shorter and shrink down, at least in this sideways view in the direction it's moving. It doesn't shrink in the diameter of it, right? It's just in the direction of motion as we're sending our spaceship from Earth to, say, Alpha Centauri, like the last example. Interestingly, though, from inside the spaceship, which now you can see how big the spaceship is for the astronaut has plenty of room to move around within the spaceship. The astronaut is at rest relative to the spaceship, but it looks like Alpha Centauri and the Earth are instead flying by at a super quick speed. If the spaceship appears to be at rest, everything else is just moving. Well, if that's all moving at a great speed, it has that length, or the distance between them, is going to be contracted. So that contracted length is noted with an L, and it's relative to the proper length L sub 0, which is measured in the rest frame, where Earth and Alpha Centauri are assumed to be at rest relative to each other. So we get that the contracted length is equal to the proper length times the square root of 1 minus speed squared divided by c squared. And so this tells us how lengths can contract depending on who's observing what. So let's look at an example of this, the contraction of a spacecraft. An astronaut, using a meter stick that is at rest relative to a cylindrical spacecraft, measures the length and diameter to be 82 meters and 21 meters respectively. The spacecraft moves with a constant speed of 0.95 c relative to the Earth. What are the dimensions of the spacecraft as measured by an observer on Earth? And remember, based on Earth, it sees the spacecraft moving very quickly, so it should see a shorter distance. The astronaut is measuring distances with the meter stick that's at rest relative to the spacecraft, right? The meter stick isn't flying through the air. And so this gives us the proper lengths, L0, of the length and diameter of said spacecraft. So that keys us into how we want to solve the equation, that we do want to set it up to be solving for the contracted length, L, relative to the proper length of 82 meters. That's almost a football field, right? The full length of the spaceship times the square root of 1 minus the speed of the spaceship, 0.95 c divided by c and squared. And what this comes down to is the spaceship now looks like it's 26 meters long. That's, just a fraction of what it was before, maybe a third of that. So it appears to be significantly shorter as observed from Earth. This doesn't mean that the astronaut feels compressed, right? For the astronaut's observation, it still is 82 meters long. But from Earth, it now looks shorter. The diameter, interestingly, stays the same. It's still 21 meters. Why is that? Well, it's not moving side to side. It's just moving in a straight line path. And the length will only contract in the direction of motion. So that's our other relativity consideration, interesting implications, and length contraction and time dilation actually work together so that things become a little less weird. There are still some weird side effects, as I mentioned, things like the twin paradox. So I encourage you to check this out. There's a link here to the twin paradox. It's a great explanation of both the paradox, and why it does work, but it's some strange stuff. So this is a great thing if you want to puzzle over it and puzzle everyone you know. Very fun stuff. Okay, please feel free to ask questions in the discussion. I'd love to discuss this further.